Hello and welcome to a brief series on applications of exponential functions. In this series, we are going to cover population models, finance applications, and finally Newton's law of cooling. And in this first video, we are going to tackle the population models. So exponential functions are very popular models to use, and the next slides in this video, as well as in the series, are going to be used for phenomena that are usually described with exponential functions. So our first population model is the Malthusian model, and this is named after Reverend Thomas Malthus. And this appeared in an essay on the principle of population in 1798. And this particular essay had a hand in passing the Census Act in 1800 in Great Britain, leading to a national census beginning in 1801. The Malthusian model has a very simple structure. It is modeled by P of t equal to P naught, or P sub 0. It'll be referred to as P naught in this series. So we have P naught times E, that's that 2.718 number, and that E number is raised to the kt power. So P of t represents the amount at time t, P naught represents the initial amount, or the amount at time 0, K represents the rate of growth if K is positive, or the rate of decay if K is negative, and T is time. On this slide, we have two curves. One is a growth curve and the other is a decay curve. So the one on the left is a growth curve, and that is the kind of curve that you would see if you had a positive k value in the exponent, where the one on the right is a decay curve, and this is what the curves would look like if you had a negative k value in the exponent. And this is a very popular model. In fact, this same model can be used to describe the following. It can be used to describe half-life in chemistry. It can be used to describe continuously compounding interest from business applications. It can also be used to describe population models for bacteria or viruses in epidemiology. Another population model is the logistic model, and this model was derived by the Belgian mathematician Pierre Verhulst in 1838. Now, he believed that the rate at which the population grows is related to the population density, so his model considered not only birth rates, but death rates as well. Now, the original model that he came up with is given here. We have P of t is equal to P naught times m, and that product is going to be divided by the sum of P naught with k minus P naught times e to the negative kt power. So P of t represents the amount after time t, P naught represents the initial amount, the amount at time 0, m represents the amount sustainable in the environment. This is also known as the carrying capacity. Little k represents the rate of growth, and t represents time. Now notice in this model, the exponential always has a negative in front of that k. Now if we consider this model, we can divide out the initial population P naught, and we'll have a simpler version that's used by TI-8384 calculators. Also, this version is introduced to students in pre-calculus because it has fewer quantities. So we can use the model P of t is equal to m divided by the sum of 1 plus b times e to the negative kt. And this b value is m minus P naught divided by P naught. Now, some things to note about the logistic model is that if the amount exceeds the carrying capacity, then the amount will decline until it reaches that carrying capacity. If the amount starts less than the carrying capacity, then it will grow until that carrying capacity is reached. Now, little k represents the maximum rate of growth, and the curves for logistic models are often called sigmoidal due to their S shape. And again, this is a very popular model. Logistic models are often used in the following situations as well: population dynamics when the environment offers limitations, spread of information in a closed environment, like advertising in a building, spread of disease in a closed environment, like maybe a college campus of some kind. So here's what a typical logistic function graph looks like. Here we can see the S-shaped curve. And in this particular curve, we have a carrying capacity of 10. That's the numerator in our function here. And here we can see that it grows pretty quick until we get to about 5. After we get to about 5 on the x-axis, the curve really doesn't grow very fast at all. It's because a lot of the environment has been taken up. There's not a lot of room left to grow. So the population growth kind of gets less and less. But here is an example of a logistic curve that actually began above its carrying capacity. And when that occurs, we can see that the graph decays immediately toward that carrying capacity. Here's another example of a logistic curve, but this time the initial amount was 8. Okay, and that means that when I start my clock at t equals 0, the curve has already taken up a lot of the environmental space. So there's not a whole lot of growth left to occur, and that's why the growth rate is pretty slow. And this concludes our first video on exponential model examples dealing with populations. In our next one, we are going to pick up with finance applications. This will include the interests that you see here and applications with annuities.